in the spring of 1960 at the National Radio Astronomy Observatory in Green Bank, West Virginia. A young astronomer named Frank Drake pointed a radio telescope toward two nearby sun-like stars and listened. The machine was not especially grand by later standards, and the room around it was quiet, practical, almost ordinary. Yet the thought behind the act was extraordinary. For the first time, someone was not merely wondering whether another intelligence might exist somewhere in the dark. He was trying to hear it. If you place yourself there for a moment, not among cinematic screens or glowing science fiction machinery, but among paper, wires, and long hours of disciplined patience, the question begins to change character. It feels less like fantasy, and more like the edge of a real experiment. What made that moment so important was not that it produced an answer. It did not. What changed was something deeper. A question that had lived for centuries in philosophy, religion, poetry, speculation, and private wonder was being translated into method. What frequency should you choose? Which stars are worth your time? What kind of signal would nature produce on its own? And what kind might suggest intention? The mystery was no longer only whether we were alone. It was whether a species like ours could learn to distinguish hope from evidence, longing from structure, silence from the faint possibility of reply. That distinction has shaped every chapter of this story. Again and again, human beings looked outward and thought they saw company. Lines on Mars seemed to hint at design. Strange radio pulses briefly carried the flavor of intelligence. Chemical traces on alien worlds leaned toward life, then slipped back into uncertainty. And with every false alarm, every disputed result, every instrument that revealed more than the eye ever could, the search became both more disciplined and more unsettling. The universe grew larger, richer with planets, more hospitable in possibility, and yet still it withheld the one answer people wanted most. So this is not only a story about alien life, it is also a story about perception, patience, and the habits of mind required to face an immense silence without filling it too quickly. As the universe opened and the evidence slowly changed, what did scientists actually learn to look for? And why has the question remained so difficult to answer in a cosmos now known to be crowded with worlds? What would it finally mean to know that we are not alone? Step far enough away from the electric world, and the sky begins to change its voice. Houses and streets retreat into a practical dimness. The familiar scale of human life loosens. At first, you notice only the brighter stars, the easy ones, the points that seem steady enough to have been placed there long ago and left untouched. But if you keep standing there, the darkness deepens. More lights emerge. The black between them grows larger. The sky stops feeling like a ceiling and starts to feel like depth. In that stillness, one of the oldest human questions arrives almost without being summoned. Are all of those lights merely lights? Or are some of them places? And if they are places, why should this small inhabited world be the only one in all that reach of dark? The question may sound modern when phrased in the language of astronomy, but the sensation behind it is far older than telescopes, older than laboratories, older even than the modern idea of science. Long before anyone knew what a star really was, human beings were already trying to decide what sort of universe they lived in. Was it a carefully enclosed order, with Earth fixed at its meaningful center, or something larger, stranger, and less intimate? Did the heavens exist for human beings to study, fear, worship, and interpret? Or Were human beings only one local occurrence inside a reality too vast to have arranged itself around their lives? The night sky can produce wonder, but it can also produce a quieter and more unsettling emotion. It can make even a settled world feel provisional. In the ancient Mediterranean, these questions began to take on sharper intellectual form. Among the thinkers who pushed furthest were the atomists, especially Democritus and later Epicurus, who imagined a universe made not of symbolic perfection, but of matter and void. The world, in this view, was not a unique moral centerpiece suspended inside a special celestial order. It was one formation among many, assembled from the same basic stuff as everything else. The Roman poet Lucretius, writing in the 1st century BCE and drawing on Epicurean thought, gave this idea one of its most haunting expressions. If matter is infinite and the void unbounded, he argued, why should only one world have formed? Why should nature perform so great a work only once? That did not amount to science in the modern sense, and it is important not to blur the difference. Epicurus and Lucretius had no telescopes, no atmospheric chemistry, no stellar physics, no concept of galaxies or planetary systems. What they had instead was a way of thinking daring enough to resist making Earth singular simply because it was home, in a culture that often treated the heavens as ordered, meaningful, and fundamentally different from the world below. The atomists proposed continuity. The same nature operated everywhere. The same principles applied beyond the visible horizon. If that was true, then many worlds became more than a poetic possibility. They became, at least philosophically, difficult to rule out. Set against this was another inheritance that would shape Western thought for centuries. In the Aristotelian cosmos, reality was finite, layered, and complete. Earth sat at the center, not necessarily as a place of emotional privilege in every sense, but as part of a structured whole in which each thing had its proper motion and proper region. The heavens were not made of the same imperfect material as the world below. Their motions expressed a higher regularity. In such a universe, the very idea of many worlds was hard to formulate. A complete cosmos did not seem to require copies of itself. It was one order, not an endless multiplication of orders. So the question of whether we are alone was never only a biological question. It was a question about what sort of reality this was in the first place. That distinction mattered because cosmology, philosophy, theology, and human self-understanding were not cleanly separate domains. A claim about the number of worlds could also be a claim about purpose, hierarchy, causation, and meaning. If there were many worlds, what did that imply about the status of this one? If beings existed elsewhere, what might that say about the place of human beings in creation? If Earth was only one local arrangement in a vast universe, then familiar intuitions about centrality and importance might need to be reworked. Even where these conclusions were not drawn directly, the pressure was already there. A universe with many worlds felt different. It changed the emotional atmosphere in which people imagined themselves living. For long stretches of time, the matter remained unresolved, not because nobody cared, but because the available evidence could not move the debate decisively. The sky was still a surface of appearances. Careful observers saw wandering planets, eclipses, comets, seasonal stars, but none of this could tell them what a star truly was, or whether worlds moved around it. So the question lived in argument, analogy, and metaphysical preference. From a modern distance, that can seem abstract. In its own time, it was intimate. The structure of the cosmos shaped how one understood providence, mortality, knowledge, and destiny. Whether there was one world or many was not an idle curiosity. It was a way of deciding what kind of home existence itself might be. As the classical world gave way to late antiquity and the medieval centuries, the plurality of worlds did not disappear. It shifted into new forms of discussion. Christian theology inherited much of Greek cosmology while also bringing its own commitments about creation, divine power, and sacred history. The result was not a single unified position. Some thinkers argued that an omnipotent God could, in principle, create multiple worlds. Whether or not he had chosen to do so, others treated the universe as a single ordered creation, coherent precisely because it issued from one divine act. Historians are careful here because later retellings often flatten the past into a simple war between religion and possibility. The historical reality was subtler. The question of many worlds could be constrained by theology, but it could also be explored within theology. What remained constant was the sense that this was no small matter. A single inhabited world preserved a certain intimacy between humanity and cosmos. It allowed the visible heavens to remain ordered toward a recognizable center. A plurality of worlds, especially if imagined at great scale, strained that intimacy. It did not necessarily abolish meaning, but it redistributed it. Human beings might still matter, but not because the universe had been built so obviously around their location. This quiet displacement of centrality would become one of the deepest undercurrents in the whole history of the subject. Every later discovery, from telescopes to exoplanets, would press on it in some form, but the pressure began long before the instruments arrived. Then the visible sky began to change, not physically, but intellectually. Copernicus did not prove that life existed elsewhere, nor that stars were suns with planets of their own. What he did was alter the stage. Once Earth became a moving world rather than the fixed center of celestial motion, the imagination loosened. The ground no longer felt quite so final. Earth had become one body among others, and that subtle shift made old possibilities easier to breathe. Few figures stand in that opening with more symbolic force than Giordano Bruno. He is often turned into a simplified modern hero, a martyr for science who proclaimed an inhabited universe and paid for it with his life. The real history is more difficult and more revealing. Bruno did imagine an immense universe filled with innumerable worlds, and he did help give the plurality of worlds a new language of emotional vastness. In his writing, the stars were no longer tiny lamps fixed to a near boundary. They could be suns, scattered through an immeasurable cosmos, and their worlds might be as real as ours. The universe ceased to feel like a closed chamber and began to feel like abundance without edge. Yet Bruno was not a modern astrophysicist before his time, and his condemnation cannot be honestly reduced to one bold thought about alien life. He was a philosopher, a former friar, a religious dissenter, a restless and provocative mind moving through the fractured confessional world of late 16th century Europe. His conflicts with ecclesiastical authority involved multiple doctrines and disputes, among them the Trinity, the soul, Christ, and sacred authority. Historians emphasize this not to diminish him, but to place him correctly in his own century. The plurality of worlds mattered deeply in his thought, but it was woven into a larger and more unsettling vision of reality. What made him important for this story was not evidence. It was scale. He gave the old possibility a grandeur from which it would not easily retreat. In Bruno's universe, the human condition changed size. The stars ceased to be distant ornaments and became possible neighborhoods of being. Creation, if one still used that word, no longer felt like a single theater built around one drama alone. That enlargement was exhilarating, but it came at a cost. Once the universe becomes truly immense, human significance can no longer depend on position. It must be defended in some other way, transformed, or surrendered. This is one reason the idea of many worlds has always carried more than scientific interest. It asks not only what lies beyond Earth, but what becomes of us when the answer no longer revolves around our location. Even then, nothing unfolded in a straight line. Johannes Kepler, one of the great architects of the new astronomy, did not simply march in Bruno's direction. He helped dismantle the old Earth-centered cosmos in one sense, yet resisted Bruno's infinite universe in another. Kepler could imagine other worlds. He sometimes played with what life under different celestial conditions might be like. Yet he also wanted the universe to remain mathematically ordered and intelligible as a designed whole. That tension is worth lingering over. Scientific change did not erase metaphysical struggle. It intensified it. Then came the telescope, and with it a new instability of appearances. The moon, once easily imagined as smooth and perfect, revealed roughness, mountains, shadow, and topography. It began to look, in an unsettling way, like a place. Jupiter acquired moons of its own, a miniature system that quietly weakened the intuition that everything must circle Earth. These discoveries did not prove inhabited worlds. They did something subtler and perhaps more important. They made comparison unavoidable. The heavens no longer seemed wholly unlike the earthly realm. This was the beginning of a long change in the emotional texture of the sky. To look upward no longer meant looking at a sealed order beyond ordinary nature. It increasingly meant looking at other worlds, whether known, suspected, or imagined. The old philosophical question gained observational edges. The moon had mountains. Planets were globes. Stars might not be tiny fixed lights after all. A universe once understood as singular and symbolically arranged was becoming materially plural, or at least open to plurality. Still, the deepest significance of this first movement lies not in any one thinker or doctrine, but in the interior shift it produced. Once people had seriously imagined that Earth might not stand alone, the sky could never quite return to innocence. Even when evidence remained thin, even when theology reasserted order, even when philosophers argued for a finite cosmos, the thought had entered human consciousness and stayed there, somewhere beyond sight. Perhaps there were other worlds, somewhere beyond those worlds, perhaps other minds. The question might sleep for a while in poetry, controversy, or quiet speculation, but it would not vanish. It had altered the silence around it. So the story begins not with proof, but with permission. Permission to think that the universe may be larger than custom allows. Permission to imagine that Earth is not the only place where life has unfolded. Permission to feel how disturbing such freedom can be. Before radio signals, before Martian soil experiments, before atmospheric chemistry and alien planets, there was this first widening of the mind under the pressure of the stars. The darkness above no longer enclosed a single complete order. It opened, and once it opened, imagination moved into the gap before evidence could catch up. The next phase of the story would belong to that unstable territory where observation, desire, language, and error began to mingle. and where the human hunger for company started to see far more in the heavens than the heavens had yet agreed to give. Once the mind had been given permission to imagine other worlds, the next temptation arrived very quickly. People began to look upward, not only with curiosity, but with expectation. The old philosophical possibility did not remain suspended in abstraction for long. It drifted down into drawings, public lectures, telescope eyepieces, newspaper columns, and private habits of looking. If other worlds existed, perhaps the signs were already there, faint but legible, waiting for the right eye to notice them. In that sense, this part of the story is not just about mistaken claims. It is about how easily possibility becomes pattern. The 19th century was especially fertile ground for that transformation. Europe and America were living through an expansion of print culture, scientific prestige, and public appetite for marvels. Astronomy held a curious place in that world. It was respected enough to borrow authority from, mysterious enough to invite wonder, and distant enough that almost no ordinary reader could directly test what he was being told. A report from the heavens arrived clothed in technical difficulty, measurements, diagrams, and astronomical language could create the feeling of rigor even when the underlying claim remained unstable. The farther away the object, the more power imagination retained. That combination burst into view in 1835, when readers of the New York Sun were presented with a series of startling reports about the moon. The articles claimed that the astronomer John Herschel, observing from the Cape of Good Hope with an astonishing telescope, had discovered lunar landscapes, vegetation, animals, and even winged humanoid beings. The descriptions were vivid enough to feel almost reportorial, and the articles carried just enough scientific texture to make disbelief harder than it might seem from a modern distance. Some readers were skeptical, many were delighted. Others seemed to have hovered between the two, enjoying the spectacle while wanting it to be true. The moon hoax, as it later came to be called, is often remembered as a charming oddity, but it revealed something more durable than a single newspaper prank. It showed how strongly people wanted the heavens to become inhabited in a way that could be pictured. Historians still differ over how much satire Richard Adams Locke intended, and how much of the episode's success depended on readers willingly leaning into belief. But the larger pattern is clear. Once populated worlds had entered the public imagination, evidence no longer needed to be strong in order to feel satisfying. A thin layer of scientific language, laid over vivid imagery, could carry astonishing weight. That same desire soon attached itself to a real planet. Of all the known worlds, Mars exerted a special pull. Venus hid behind cloud. Mercury stayed too close to the sun. The outer planets seemed too remote and severe to imagine comfortably as scenes of life. Mars was different. It showed dark markings. White caps appeared and retreated near the poles. Its day was not radically unlike Earth's. Its seasons seemed legible. Through 19th century telescopes, it looked not like a point of light, but like a place with changing conditions. To a generation eager to find company without leaving the solar system, it was the most persuasive candidate. This did not mean astronomers abandoned discipline and plunged directly into fantasy. Many observed Mars carefully, but the planet encouraged a style of reasoning that moved easily from resemblance to inference. If Mars had polar caps, perhaps it had water. If dark regions changed with the seasons, perhaps there was vegetation. If its surface looked severe, perhaps life there had adapted in unfamiliar ways. Or perhaps intelligence had arisen under pressure. Such thoughts gained force because they did not feel wholly absurd. They lived in that dangerous middle zone where a few real similarities can lend too much credibility to what remains unknown. The turning point came during the favorable opposition of Mars in 1877, when the Italian astronomer Giovanni Schiaparelli produced a map that would echo far beyond the observatory. Schiaparelli was not a reckless visionary. He was a serious observer, working at the limit of what his instruments and the atmosphere would allow. While studying the Martian surface, he described certain long, narrow features using the Italian word canali. In context, the word did not necessarily imply engineering. It could mean channels or grooves. Yet as the term circulated more widely, especially in English, it hardened into canals. And with that single shift, an entire layer of implication arrived. A difficult visual impression began to sound like design. Even so, it would be too simple to say the whole episode came from mistranslation. Telescopic observation of Mars was intrinsically difficult. Atmospheric turbulence, contrast effects, and limited resolution encouraged the eye to connect broken patches into lines. Different observers drew different maps. Even the same observer could return on another night and see a different structure. Schiaparelli himself could be cautious in one context and suggestive in another. The conditions were ambiguous enough to invite geometry where perhaps there was none, and the culture was ready to reward exactly that sort of reading. Into that atmosphere stepped Percival Lowell. He was, in many ways, an unlikely prophet of Martian civilization, and therefore an ideal one. Born into a prominent Boston family, educated, wealthy, restless, and intellectually ambitious, Lowell had the means and confidence to pursue enormous questions with seriousness and style. Before devoting himself to Mars, he had written on East Asia and moved through diplomatic and elite intellectual circles. He was not an outsider shouting from the margins. He was a man of status, convinced that the heavens still held one of the great mysteries of his age. Lowell founded an observatory in Flagstaff, Arizona, partly because he wanted clear, dry air and steady seeing conditions. The work there was patient rather than theatrical. Night after night, Mars was studied, sketched, compared, and reconsidered. Lowell gradually convinced himself that the faint linear features seen by Schiaparelli and others were real, extensive, and artificial in his interpretation. Mars was an aging world drying out under cosmic time. Its inhabitants, faced with dwindling water, had built a globe-spanning network of canals to move meltwater from the poles toward the equatorial regions where life still endured. It was a vision at once scientific in surface and deeply imaginative in structure. Dim marks became the infrastructure of a civilization under stress. What gave Lowell's theory such power was not only the claim itself, but the emotional logic inside it. The late 19th century admired engineering, systems, and large technical solutions. Humans were already cutting canals through isthmuses, organizing landscapes, measuring empires, and imagining mastery through infrastructure. A Martian civilization surviving by means of continental waterworks did not seem purely fantastical in that atmosphere. It also carried a mood of melancholy refinement. Mars became not simply inhabited, but old, austere, ingenious, and threatened by decline. It mirrored modern anxieties in planetary form. Lowell wrote books, lectured widely, and helped turn the canal idea into one of the most captivating scientific dramas of the age. Newspapers amplified it. Popular audiences embraced it. Fiction drew strength from it. H.G. Wells would soon give Mars a darker destiny in the public imagination, and other writers and popularizers helped keep the planet suspended between science and vision. Mars was becoming less a distant astronomical object than a neighboring intelligence glimpsed through difficulty. Yet resistance existed from the beginning. Many astronomers could not see Lowell's elaborate network at all. Others saw some linearity, but not the geometrical system he described. E.M. Antoniadi, observing under better conditions and with better optics, increasingly described irregular patches and surface variations that the eye, under strain, might simplify into lines. Alfred Russel Wallace argued that the physical conditions on Mars made Lowell's civilization deeply improbable. Skepticism did not arrive only after the fact. It accompanied the episode while it unfolded. That is one reason the canal story remains so revealing. The contrast is not simply between a credulous public and a sober scientific establishment. It runs through the scientific community itself, and through the structure of perception. Lowell was not inventing his observations out of nothing. He was working at the edge of what instruments and eyesight could do, where expectation can complete a pattern before evidence has fully earned it. Once the mind anticipates order, faint discontinuities can fuse into a structure that feels unmistakably real. The stronger the expectation, the more persuasive the pattern can seem. There was also a deeper limitation that no telescope of Lowell's time could overcome. Astronomers were trying to answer a biological question from a distant surface seen across tens of millions of miles. They could infer seasons, brightness, color, and broad geometry, but not chemistry, not climate in any modern sense, and certainly not the living status of what lay on the ground. So analogy did much of the work. Observers asked what earthly process might correspond to some changing Martian feature. Water, vegetation, aridity, engineering, perhaps civilization. The unknown was rendered legible through familiar categories, and that legibility gave it force. By the early 20th century, the canal idea began losing scientific ground. Though it lingered much longer in popular culture, better observations weakened the geometry. The neat global network dissolved. Mars did not become empty overnight. It became uncertain again, and uncertainty is harder to romanticize. Yet the canal era left an enduring mark. It taught that the search for life elsewhere could not rest on vision alone, or on the analogies vision made so tempting. And still, something survived the collapse. The larger hunger did not disappear. If anything, disappointment clarified the stakes. People had learned that wanting company could make the universe seem more forthcoming than it really was. A higher standard of evidence would be needed. The sky would have to be approached with less projection and more discipline. That adjustment did not happen all at once. Public culture continued feeding on inhabited worlds, and astronomers remained divided on many details of planetary habitability. But the direction of travel had begun to change. If intelligence existed elsewhere, perhaps it would not reveal itself through faint surface markings at all. Perhaps the sign would have to come through another medium, another method, another idea of what evidence should look like. The heavens, after all, were not only there to be seen, they could also, in principle, be heard. And in the century to come, that possibility would begin turning the old question away from imaginative vision and toward deliberate search. So the sky, long treated as something to look at, began to suggest another possibility. Perhaps vision had been the wrong sense to trust by itself. A planet's face could mislead. A line could become a canal simply because the eye wanted to complete it. If intelligence existed elsewhere, perhaps it would not reveal itself through dim markings spread across a distant disk. Perhaps it would appear in a form less entangled with imagination. Perhaps the universe would have to be listened to. By the middle of the 20th century, that thought no longer belonged only to fiction. Radio had transformed modern life and then transformed astronomy. Techniques refined through communications and war had opened regions of the cosmos ordinary sight could never reach. Invisible wavelengths, once beyond human awareness, were becoming data. The universe grew stranger in the process. It had bursts, lines, emissions, static, signatures. It was not silent in any simple sense. And once astronomers learned that space was full of radio phenomena, another question followed almost naturally. If nature could produce radio waves, could intelligence use them too? That question found its first influential expression in 1959 in a short Nature paper by Giuseppe Cocconi and Philip Morrison. The paper was remarkably brief, calm in tone, almost austere in confidence. It did not claim that extraterrestrial civilization had been detected. It did something more consequential. It argued that interstellar radio communication was scientifically reasonable to search for. Across centuries, the idea of other minds beyond Earth had wandered through philosophy, theology, astronomy, satire, and fiction. Cocconi and Morrison brought it into a new register. They treated it as a technical problem. Their reasoning was elegant. Radio waves could travel vast distances. Certain frequencies might stand out as natural meeting points for any civilization familiar with physics. Among them was the spectral line associated with neutral hydrogen, the most abundant element in the universe. Hydrogen was not a local curiosity. It was universal. Any technologically capable society studying the cosmos would know it. If one wanted to choose a frequency, another civilization might independently recognize as special. Hydrogen offered a plausible common reference. The paper did not promise success. It simply removed the idea from the realm of vague longing. There was, as they put it, no insuperable difficulty. That phrase mattered because it changed the emotional status of the search. Once a problem is described in terms of apparatus, wavelength, and signal strategy, it begins to feel less like hope and more like work. There is a distinct threshold here. Many scientific shifts begin when a question ceases to be merely interesting and becomes operational. What do you point at? How long do you listen? What kind of transmission might nature produce on its own? And what kind would look improbable enough to matter? A culture that had spent decades imagining Martian civilizations through the telescope was being asked to consider a more disciplined possibility. Forget the visible surface for a moment. Suppose intelligence announces itself through structure. No one embodied that term more clearly than Frank Drake. He was young, technically gifted, imaginative without being theatrical, and unusually comfortable at the border between enormous questions and practical procedure. Those who knew him often described a mind at ease with very large problems, but also with the patience required to approach them properly. He had served in the Navy, trained in astronomy, and come of age in a world being reshaped by electronics, radar, radio astronomy, and space-age ambition. He did not approach extraterrestrial intelligence as a mystic or as a publicist. He approached it like an engineer of uncertainty. In 1960, at Green Bank, Drake put the new logic into practice through an experiment that would later acquire almost mythic status, though in the moment it was modest. Very quiet, and somewhat improvised. He called it Project Ozma, borrowing the name from the ruler of El, Frank Baum's Land of Oz. The choice carried a trace of playfulness, but the work itself was serious. Using the observatory's 85-foot Tatel radio telescope, Drake selected two nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened near the hydrogen line. They were not random targets. They were close, familiar and stellar type, and therefore reasonable places to begin if one had only a small patch of sky and limited time. Looking back, it is easy to give the moment more theatrical grandeur than it possessed. There was no immediate revelation out of the dark. Much of the experience consisted of calibration, instrumentation, interference checks, and patience. That was part of the transformation. Extraordinary hopes were now being forced through ordinary scientific procedure. Any suspicious signal had to survive the possibility of terrestrial contamination, instrumental artifact, or natural astrophysical origin. Early on, one strong signal briefly drew attention before proving local rather than interstellar. Even that was useful. Listening had brought with it new forms of disappointment. Yet Project Ozma marked a boundary that never quite closed again. For the first time, someone had not merely suggested that the search could be done. Someone had done it. A radio dish had been pointed deliberately toward other stars with the explicit aim of finding signs of intelligence. The result, in one sense, was silence. In another, it was the birth of a field. Silence in this context was not emptiness. It was data gathered under a method. Once that happened, the subject could no longer be dismissed so easily as an unstructured dream. There was also something subtly revolutionary in the kind of sign Drake and his contemporaries were seeking. They were not looking for life in the broadest sense. A bacterium on another world would not send a narrowband radio transmission. A forest would not choose the hydrogen line. Early SETI was looking for technology, intention, and a patterned emission difficult to attribute to anything but agency. That narrowed the question and enlarged it at the same time. Narrowed it because most living things would leave no such trace. Enlarged it because now the inquiry reached beyond biology toward minds capable of physics, engineering, and communication. The difference is worth dwelling on. Earlier eras had imagined other beings through landscapes, canals, climates, invisible surfaces. Radio SETI introduced a different kind of common ground. It assumed that physics offers a shared language. Even if the speakers are utterly unlike us, their bodies, senses, cultures, histories, and chemistry might be radically different. None of that would erase the hydrogen line. None of it would repeal electromagnetism. Beneath all the possible weirdness of life, there remained a common substrate of physical law. That was the quiet confidence inside the early search. Not that extraterrestrials would think as humans think, but that any technological civilization must in some way confront the same universe. A year after Project Ozma, the question acquired another durable form. In 1961, a small group of scientists gathered at Green Bank to discuss the prospects for detecting intelligent extraterrestrial life. The meeting was modest in scale, almost intimate by later standards, but it proved historically influential because Drake arrived with a practical problem. The subject was enormous. The unknowns were everywhere. Conversation could easily dissolve into unsupported guesswork. So, as a kind of agenda on a blackboard, he wrote what would later become famous as the Drake equation. Its later celebrity can be misleading. People often encounter it as though it were an oracle, a device for calculating the number of communicative civilizations in the Milky Way. At birth, it was something more useful and more modest. Drake broke the larger mystery into linked factors: the rate of star formation, the fraction of stars with planets, the number of potentially habitable planets per system, the fraction on which life arises, the fraction on which intelligence evolves, the fraction that developed detectable technology, and the average length of time such civilizations remain communicative. The equation did not solve the mystery, it arranged it. That was a conceptual triumph, even before any numbers were agreed upon. One could argue about planets, or about the origin of life, or intelligence, or technological longevity, and still remain inside a common frame. A single overwhelming question had been turned into a research program distributed across astronomy: biology, planetary science, evolution, and time. The unknown had not been conquered, but it had been divided into parts that might one day yield. And sometimes that is what changes a field. Not an answer, but a better shape for the question. With the Drake equation, the search for extraterrestrial intelligence stopped feeling like a single leap into darkness and began to resemble a set of interlocking inquiries. How common are planets? How readily does chemistry become biology? Does intelligence arise often or rarely? How long do technological societies remain detectable? At the time, nearly every term in the equation was deeply uncertain, but uncertainty handled in pieces feels different from uncertainty treated as fog. The Green Bank meeting made the vastness negotiable. The broader cultural atmosphere mattered too. The early 1960s were saturated with cosmic ambition. Spaceflight was no longer a fantasy. Satellites orbited Earth. Electronics and communications had changed what humans believed they could build, transmit, and intercept. Against that background, listening for extraterrestrial intelligence no longer sounded quite as bizarre as it might have a generation earlier. It still sounded bold, certainly, but it had entered a world already convinced that the sky had become technologically available. At the same time, the field retained a curious emotional tone. For all its seriousness, early SETI still had room for humor, eccentricity, and intellectual play. The name Ozma signaled that. So did Drake's ability to speak about extraterrestrial civilizations without sounding embarrassed or grandiose. That balance mattered. And it would matter even more as the field matured. The search required people able to hold wonder and restraint at once. It required something else as well: tolerance for emptiness. Much of science advances through positive findings, but some of its most mature forms are built through repeated non-detection, handled with care. Radio SETI would become one of those disciplines. You listen, and you mostly do not hear what you hope to hear. Or rather, you hear many things, but almost all of them dissolve under scrutiny into interference, natural sources, or ambiguities too weak to bear the meaning briefly placed on them. That kind of work demands a peculiar temperament. One must remain open to astonishment while being professionally committed to disappointment. Still, once humanity crossed this threshold, the old question was altered beyond recovery. It could no longer live only in philosophy, poetry, or planetary romance. It had entered the laboratory, the observatory, the receiver, the conference room. It had acquired frequencies, targets, criteria, and error bars the universe had not yet answered. Perhaps it had not even noticed. But human beings had changed their posture toward it. They had ceased merely to wonder whether someone might be out there and had begun. in a literal sense, to check. And that change would have consequences far beyond the quiet hours of Project Ozma or the chalk marks of Green Bank. Because once you define what a meaningful signal might look like, strange emissions begin to matter differently. Unusual regularities gain a sharper edge. Anomalies become occasions for both excitement and discipline. Somewhere in the years ahead, the instruments would pick up patterns that seemed, for a moment, almost too exact, too deliberate, too unlike the usual noise of the cosmos, and the search would learn in a more intimate way how easily hope can flare inside a line of data. Once scientists had taught themselves to listen for intelligence, the universe offered a new kind of temptation. A mark on Mars could be argued over for years because it sat at the edge of sight, blurred by distance and desire. Radio data felt different. A signal could be measured, timed, recorded, replayed. It seemed cleaner than vision, less vulnerable to the old habit of seeing what one wished to see. Yet that confidence carried its own danger, because pattern has a special power over the mind. A narrow band spike, a regular pulse, a sequence that repeats at exactly the right interval does not merely attract attention. It suggests intention, and once intention enters the frame, imagination can move very quickly. That lesson arrived with unusual force in Cambridge in 1967. The instrument involved was not a gleaming dish aimed heroically at a famous star. It was a large radio array built for another scientific purpose entirely: the study of interplanetary scintillation, the flickering of compact radio sources caused by the solar wind. The apparatus covered acres, with wires, poles, and long runs of receiving elements spread across the ground. At the center of the episode was Jocelyn Bell, later Jocelyn Bell Burnell, then a graduate student who had helped build the instrument and spent long hours examining its chart recorder output by eye. That detail matters. The discovery did not begin with a dramatic anomaly flashing across a modern screen. It began with paper, an enormous amount of it, marked by the restless texture of radio data. Bell learned the ordinary habits of the instrument so thoroughly that she could recognize when something did not belong. Amid expected patterns, she noticed a bit of what she called scruff, a signal too brief and too odd to fit the usual categories. Then it returned, and returned again. It always appeared at the same sidereal time, which meant it tracked the stars rather than the Earth's human schedule. That one fact pushed the source beyond the obvious terrestrial explanations. Whatever was producing the pulses seemed tied to the sky. Imagine the atmosphere of that moment. Not certainty, not revelation, but a tightening of attention. Bell, her supervisor Anthony Hewish, and others in the group had to decide whether they were dealing with interference, instrumental error, an unfamiliar astrophysical phenomenon, or something stranger still. The pulses were remarkably regular. They arrived every 337 seconds, sharp and repetitive in a way that did not resemble most known radio phenomena. For a brief period, partly in jest and partly in acknowledgement of the unsettling neatness of the signal, the source acquired the nickname LGM-1 for Little Green Men. The nickname has endured because it captures the borderland between scientific caution and human reflex. Even when investigators are disciplined, even when they know how often anomalies collapse under scrutiny, the thought can still flash across the mind. If a signal is too exact, too oddly artificial seeming, one almost cannot help entertaining the possibility. In this case, the idea was never treated as a public conclusion. nor even as the most likely explanation among serious researchers. But it was present enough to shape the emotional temperature of the investigation. That alone is revealing. What followed is one of the best examples in the history of science of how astonishment is supposed to behave when handled well. The Cambridge group did not stop at the shock of regularity. They kept searching. Soon they found more such sources in other parts of the sky. That changed everything. A single odd transmitter might, at least in imagination, hint at intention. Several distributed across the heavens and showing related behavior pointed elsewhere. The explanation that took hold, and quickly proved persuasive, was that these were natural objects rather than engineered beacons. Rapidly rotating neutron stars, the collapsed remnants of massive stars, sweeping beams of radiation across space like cosmic lighthouses. To modern ears, pulsars already sound exotic enough that it can be easy to miss how disruptive they were at the time. Neutron stars had been theorized decades earlier, but here was a new class of object behaving with astonishing precision. Nature, it turned out, could generate regularity that looked almost designed if one had not yet seen its mechanism. The signal's very artificiality was the lesson. Order, even extreme order, does not belong only to minds. The universe contains processes capable of producing patterns we are tempted to reserve for intelligence. Bell herself remains central to this story for reasons beyond the technical discovery. There was a steadiness in her role that later observers have often admired. She noticed what others might have dismissed, kept returning to it, and separated signal from clutter through persistence rather than grand intuition. The later Nobel Prize controversy, in which the 1974 award went to Hewish and Martin Ryle, but not to Bell, belongs to a broader history of credit, hierarchy, and gender in science. It need not dominate this section, but it does deepen it. One of the most important episodes in the search for extraterrestrial intelligence was shaped by a young researcher whose discipline helped prevent a spectacular misreading. The Pulsar episode clarified something essential. It is one thing to imagine that a technological civilization might send a radio message. It is another to discover that unfamiliar astrophysical sources can mimic some of the qualities one expected intelligence to display: narrowness, repetition, regular timing, salience. None of these, on their own, could guarantee agency. From then on, any claim that a signal might be artificial had to survive a harder comparison with a universe now known to contain bizarre and surprisingly orderly natural phenomena, far from making the field less interesting, that made it more intellectually alive. A serious search matures when it learns what can go wrong. Early radio SETI had gained legitimacy by becoming an experiment. Now it gained maturity by encountering one of the most seductive false trails imaginable and navigating it without losing its standards. The pattern would repeat. A strange signal would appear. Imagination would flicker, and procedure would close in. And then, every so often, one would remain. A decade after the first pulsars were identified, another radio event entered the history of this question with a different mood, less explanatory and more unresolved. On the night of August 15th, 1977, at the Ohio State University Radio Observatory, known as Big Ear, a powerful narrowband signal was recorded during a SETI survey. The telescope itself was unusual, fixed rather than steerable in the way many people imagine radio observatories. It relied on Earth's rotation to sweep its beam across the sky. The data emerged as columns of characters representing signal intensity. Days later, when astronomer Jerry Eman was reviewing the printout, One sequence stood out so strongly that he circled it and wrote a single word in the margin. Wow. The signal lasted 72 seconds. Exactly the sort of duration Big Ear would have captured from a stationary celestial source, passing through its beam. It appeared near the hydrogen line, close to the region long considered attractive for interstellar communication. It was unusually strong. It did not fit comfortably into the background. And because it arrived in the right place, at the right sort of frequency, with the right sort of brevity and intensity, it acquired a peculiar status. Not proof, not even close, but enough to endure in memory. There is a special category of scientific event to which the wow signal belongs. It is neither a discovery nor a debunked mistake, but an unresolved occasion. Those can be harder to live with than either certainty or error. If a signal is quickly explained as local interference, the mind relaxes. If it is confirmed again and again, the field reorganizes around it. But when something promising appears once and never returns, it produces a more durable discomfort. The data remain. The interpretation does not settle. Possibility survives analysis by failing to become either history or illusion. Over the years, many suggestions have been offered. Could it have been terrestrial interference, despite the apparent evidence pointing skyward? A satellite transmission not recognized at the time? A rare astrophysical event? A reflection? A cometary explanation? A quirk of instrumental circumstance? Different ideas have drawn attention at different times, but none has won broad consensus. The signal's real power may lie in exactly that state. It was good enough to matter, but not good enough to carry the weight people wanted to place upon it. This is where non-confirmation becomes central. Unseti. Repetition is not a luxury. It is one of the foundations of credibility. A signal that cannot be found again under controlled conditions, and preferably by independent instruments, remains suspended in ambiguity. To outsiders, that can seem unsatisfying or even overcautious, but the caution is earned. The field had already learned how quickly a suggestive pattern could ignite public fantasy. It had also learned how strange nature could be on its own. By the late 20th century, responsible practitioners understood that a one-time anomaly, no matter how beautiful, could not be allowed to stand as a world-changing claim. The emotional cost of that standard should not be underestimated. It means that some of the most memorable moments in the search are moments of withholding. Someone sees something extraordinary in the data, feels the old surge of recognition, and then must proceed as though none of that feeling counts. The signal must be checked, challenged, localized, distrusted, compared. It must survive contact with the dull machinery of skepticism. There is something almost monastic in that discipline, a refusal to confuse the beauty of a possibility with the truth of it. As SETI moved forward, that discipline began to formalize itself. By the late 1980s, and then in revised form later, researchers associated with the International Academy of Astronautics and related groups developed post-detection protocols. These were not laws, and they could not guarantee agreement. But they expressed an important cultural shift. A possible detection of extraterrestrial intelligence was no longer imagined as a single, triumphant announcement. It was treated as an event requiring verification, transparency, consultation, and restraint. Signals would need independent confirmation. Data would need to be shared. Public statements would need care. That institutional maturity tells us something broader about science. Often the clearest sign that a field has grown up is not that it has answered its defining question, but that it has learned how to behave in the presence of a possible answer. SETI, shaped by episodes like pulsars and the WOW. Signal had begun to understand its own vulnerabilities. It knew that ridicule would be swift if it overreached. It knew that the desire for contact ran deep in the culture. It knew that history would judge not only whether it found something, but whether it preserved its standards when the most intoxicating possibility appeared close at hand. Still, standards do not remove longing. The charts, the protocols, the frequencies, the repeated caution all existed because the underlying question retained its force. If anything, the false alarms sharpened it. A good anomaly can be more haunting than a clean, null result. It leaves behind a faint afterimage, a sense that the universe has briefly arranged itself into the shape of an answer and then withdrawn. Pulsars taught that nature can sound artificial. The wow. Signal taught that ambiguity can be almost unbearable when it arrives in exactly the form one has been trained to notice. By then, the search for extraterrestrial intelligence had acquired a distinctive emotional structure. It had room for astonishment, but not indulgence. It had learned to welcome anomalies and distrust them in the same breath. It had become more procedural, more professional, and more aware that any genuine detection would have to emerge through layers of verification thick enough to cool the imagination before it reached the world. This did not make the mystery smaller. It made it harder to mistake for an answer. And yet, for all the sophistication of radio methods, another path into the question still waited. If signals from the stars could tease and then recede into uncertainty, perhaps a nearer world might yield something more tangible. Somewhere closer than Tau Ceti, or the coordinates of a one-time radio event. There was a planet that had already occupied the human imagination for generations. Now the question would return there in a different form. Not as a line in a telescope and not as a pulse from afar, but as chemistry, soil, and the difficult hope that life might leave traces in rust-colored dust. So the search turned back toward the old red planet, but in a new mood. Mars was no longer being asked to reveal civilizations through faint lines at the edge of sight, and it was no longer serving mainly as a screen for inherited hopes. By the 1970s, the question had become harder and more intimate. If life existed there, or had once existed there, could it be detected in soil? In chemistry, in the behavior of a few carefully designed experiments lowered to the surface by machines. After telescopes and radio dishes, the inquiry narrowed to something almost austere. Scoop the dust, heat it, feed it nutrients, measure the gases, watch what happens. Mars had always invited this return. It was close enough to reach, distant enough to remain alien, and similar enough to Earth that the imagination could never quite give it up. Even after Lowell's canals faded into caution, the planet kept some of its authority. It had seasons, ice, weather, and landforms that looked carved rather than abstract. It was a place where one could still ask, seriously? Whether biology had ever found a foothold. That mattered. The search for life needed a world that was not hopelessly remote. And Mars remained the nearest place where the question could be posed through direct contact rather than inference alone. By the time NASA's Viking mission took shape, planetary science had become both more ambitious and more careful. The Mariner missions had already transformed the solar system by showing how strange neighboring worlds could be. Mars, too, had been stripped of much of its romantic gloss. It no longer looked like a home of engineers tending planetary waterways. It looked cold, dry, cratered, and severe, yet that severity sharpened the challenge. If life had existed there, perhaps it was microbial. If it still existed, perhaps it persisted in forms too modest for fantasy, but not beyond chemistry. Viking would not search for cities. It would search for metabolism. There was something deeply revealing in that shift. Human beings had once tried to identify intelligence on Mars by drawing lines between uncertain marks. Now they were designing instruments to detect the faint signatures of living processes themselves. This move from visible analogy to experimental biology marked one of the great maturations in the history of the question. It also made failure feel more personal. When one misreads a planet through a telescope, disappointment remains somewhat abstract. When one sends a laboratory to another world and asks, in effect, whether anything there is alive, the answer lands differently. The Viking program carried 2 orbiters and 2 landers. And when the landers reached the Martian surface in 1976, they brought one of the most audacious life detection packages ever attempted. The biology experiments were not simple, but their intuition was clear enough. If microbes were present in the soil, perhaps they would react when given nutrients, or exposed to conditions meant to reveal assimilation or gas release. Alongside those biology experiments was a gas chromatograph mass spectrometer intended to search for organic molecules directly. Taken together, the instruments embodied a whole philosophy of approach. Let the planet speak through chemistry. Let life, if it is there, betray itself through process. One of the most intriguing instruments in that suite was the labeled release experiment, designed by Gilbert Levin and Patricia Stratt. Its method was elegant. A small sample of Martian soil would receive a nutrient solution containing radioactive carbon. If microorganisms in the soil metabolize those nutrients, they might release radioactive gas that could then be measured. On Earth, comparable tests could reveal microbial activity efficiently. Levin was a determined and inventive figure, the kind of researcher whose confidence in an idea could survive years of skepticism. He believed that if Mars harbored even simple living organisms, his experiment had a real chance of catching them in the act. When Viking ran the labeled release experiment, the result was startling. The treated soil produced a rapid release of radioactive gas, more than once. The experiment behaved in a way that, at first glance, resembled biological metabolism. For anyone who had spent years hoping the old question might finally tighten into an answer, the moment had undeniable force. This was not a line seen through a telescope, nor a signal crossing interstellar distance. A machine had fed the Martian soil, and the soil had answered. But science almost never lets one striking result stand alone. Other Viking instruments complicated the picture immediately. The gas chromatograph mass spectrometer did not detect organic molecules in the Martian soil at the levels many researchers expected would accompany biology. 2 other biology experiments, gas exchange and pyrolytic release, produced results that were ambiguous, suggestive in places, but not widely judged decisive. Then there was the broader Martian environment itself. Dry, cold, bathed in ultraviolet radiation, and apparently hostile to the preservation of simple organics near the surface. Instead of converging toward one answer, the data began pulling in different directions. That tension would define Viking's legacy. The labeled release experiment looked positive enough that Levin never stopped arguing it had detected life. Many others, including much of the planetary science community, came to a different conclusion. They suspected that the reactive behavior could be explained by oxidizing chemistry in the soil rather than biology. Perhaps ultraviolet radiation had helped generate compounds capable of breaking down the nutrient solution and releasing gas without any living cells being present? If so, Viking had not found life. It had found a planet chemically able to imitate one of life's signatures. This was exactly the kind of result that can haunt a field for decades. A clean failure would have been easier to absorb. A clean success would have transformed history. Instead, Viking produced something much harder, a result strong enough to inspire continuing belief. But entangled enough to support a non-biological explanation, many experts found more plausible. The disagreement never quite vanished because neither side could erase the part of the record that seemed to favor the other. Levin could point to the behavior of his experiment and say, in effect, that Mars had done something living soils do. His critics could point to the missing organics and the harsh environment and argue that biology had not earned the stronger claim. There is a psychological drama inside such disputes that can be easy to miss from a distance. Gilbert Levin's persistence was not just casual stubbornness. It grew out of intimate familiarity with the instrument he had designed. People who build experiments often trust certain patterns in the data because they know, in detail, how the system is meant to respond. That can be a strength, but it can also deepen attachment. For Levin, Viking was never just a historical episode. It remained unfinished evidence. A partly muffled answer the broader scientific community had declined to hear. The community, meanwhile, had its own discipline to defend. Extraordinary claims required converging evidence, and Viking had not delivered enough of it. Years later, Mars complicated the picture again. The Phoenix lander's detection of perchlorates in Martian soil opened a new line of reinterpretation, because perchlorates can alter how organics behave when heated and analyzed. Some researchers argued that Viking's failure to detect organics might not have been as decisive as once believed. That did not resolve the life question, but it softened earlier confidence that the null result had closed the case. Mars, true to form, refused to become simpler. Even retrospective analysis seemed to produce more nuance rather than less. There was another, quieter melancholy folded into the Viking story. Among the scientists involved in designing life detection strategies for Mars was the microbiologist Wolf Vishniak, who developed an experiment known as the wolf trap. Vishniak approached the problem from a different angle, focusing on detecting microbial growth in a small chamber rather than only dramatic metabolic release. His instrument was ultimately removed from the final Viking payload as the mission was pared down. Later, while conducting field work in Antarctica, Vishniak died in an accident. The combination of the lost experiment and the loss of the man himself left behind one of those small absences science accumulates without much ceremony. No one can say the wolf trap would have solved anything, but its absence remains part of the human contour of Mars exploration. By the late 20th century, Viking had become more than a mission. It had become a case study in how hard life detection really is. To search for life on another world is not simply to look for something pleasant and familiar. It is to distinguish biology from chemistry under conditions that may be unlike anything on Earth, using finite instruments, brief experiments, and incomplete context. On our own planet, living systems sit inside a rich web of environmental understanding. On Mars, the same kind of measurement exists inside a much thinner frame. A signal that might feel obvious on Earth can become uncertain on another planet because the surrounding reality is only partly known. Then, in 1996, Mars returned to the center of public attention in a new and more dramatic way. A team led by David McKay published a paper in Science on a Martian meteorite known as ALH-84001, found in Antarctica but believed to have originated on Mars. The team argued that the meteorite contained several lines of evidence potentially consistent with ancient Martian life: carbonate globules, certain organic compounds, tiny structures resembling microscopic fossils, and magnetite crystals that some compared to products of biological activity on Earth. The announcement landed with unusual force. The White House commented on it. Newspapers around the world treated it as a possible turning point. Once again, Mars seemed poised to yield something extraordinary. What made ALH-84001 so compelling was the layered structure of the claim. No single feature in the meteorite constituted a definitive fossil. The case rested on accumulation, on several suggestive pieces leaning in the same direction. That is often how ambiguous evidence gains power. If the shapes are only vaguely biological, perhaps the chemistry strengthens the case. If the chemistry remains open to abiotic explanation, perhaps the mineral textures carry more weight. Together, the pieces can begin to feel like convergence. And convergence is one of the most seductive experiences in science. But here again, Mars answered with complication. Critics moved quickly. Not because the claim was unserious, but because each line of evidence seemed capable of a non-biological explanation. The tiny structures were smaller than many known terrestrial bacteria and might simply record mineral processes. The organic compounds could have formed through non-biological chemistry or entered through contamination. The magnetite crystals, once treated as especially suggestive, no longer looked uniquely biological under closer scrutiny. Over time, the consensus shifted toward caution. ALH-84001 remained historically and scientifically important, but it did not become the first accepted proof of life beyond Earth. If Viking had shown how chemistry could imitate a living response, ALH-84001 showed how a rock could gather around itself the appearance of biology without forcing the conclusion. Together, the two episodes changed the intellectual atmosphere around Mars. They did not make life there less possible. They made the standards harder. A strong case would need more context, more redundancy, more confidence in excluding non-biological pathways. The Red Planet had become a training ground in epistemology, a place where researchers learned, sometimes painfully. The difference between exciting evidence and evidence strong enough to carry history, and still the pull of Mars endured. That endurance matters. Lesser questions fade when they remain unanswered too long. This one did not. The difficulty of the evidence kept returning scientists to the planet with better instruments. New landing sites, improved geochemistry, and a more patient sense of what detection might actually require. Mars had stopped functioning as a simple dream of neighboring civilization, but it had not become a solved biological case. It occupied a more demanding middle state. It was a world that might once have been habitable, perhaps even inhabited, yet insisted that every claim be earned under harsh conditions. There is something almost pedagogical in the way Mars behaved across these decades. Human beings approached it first through visible fantasy, then through direct experimentation, then through ancient rocks pulled from Antarctic ice. Each time the planet seemed on the verge of becoming legible, it withheld final clarity, not out of malice, of course, but because nature does not organize itself around our appetite for neat conclusions. Mars was teaching a broader lesson about the search for life beyond Earth. Evidence would rarely arrive in a form that allowed innocence. It would come tangled with geology, chemistry, contamination, instrument limits, and contested interpretation. By the end of the century, that lesson had altered the scale of the question. If nearby Mars remained this hard to read, perhaps the search could not depend only on our nearest neighbor. Perhaps the answer, if it came, would require a wider census of worlds and a much larger stage. The irony was striking. Just as Mars taught scientists how hard it was to interpret a single planet up close, astronomy was on the verge of revealing that planets themselves were not rare exceptions at all. Mars would remain important, but the question was about to expand beyond it, outward into a galaxy suddenly crowded with places where life might, in principle, begin. And so the search widened almost against its own habits. Mars had taught scientists how stubborn a single planet could be, how even close inspection could leave the central question suspended between chemistry and hope. For a long time, that nearness had shaped the imagination. If life beyond Earth existed, perhaps it would first be found next door, in soil samples, ancient rocks, or buried traces beneath a rust-colored sky. But while researchers were still learning how difficult one neighboring world could be to interpret, another part of astronomy was preparing to change the scale of the entire question. The sky was about to become crowded. For much of modern scientific history, planets beyond the solar system belonged to a strange category. They were plausible, even likely to many astronomers, but they remained unseen. Other stars shone in overwhelming numbers, and if the Sun possessed planets, it was reasonable to suspect that many distant stars did as well. Yet suspicion is not evidence. The stars were too bright, the planets too faint, the distances too great. Human beings had built intricate theories about celestial mechanics, stars, and galaxies without knowing whether planetary systems were common or rare. In one important sense, the old question still lacked a foundation. It is one thing to ask whether life exists elsewhere. It is another to know whether there are enough elsewheres for the question to carry real astronomical weight. By the late 20th century, that uncertainty was straining against new methods. Astronomers had become increasingly skilled at detecting things indirectly. A star could reveal an unseen companion, not by showing it directly, but by wobbling very slightly in response to its gravitational pull. The effect was tiny, almost painfully tiny, but spectroscopy had become sensitive enough to chase such shifts. Researchers could watch for minute changes in a star's radial velocity, its motion toward or away from Earth, encoded in slight movements of spectral lines. If the star rocked back and forth with a regular period, perhaps a planet was tugging at it. That was the method Michel Mayor and Didier Queloz used in the mid-1990s at the Haute-Provence Observatory in France. Both were careful, technically disciplined observers, and neither was searching for a mythic Earth-like twin hidden in romantic distance. They were looking for measurable regularity that could survive doubt. In 1995, they announced that they had found a planet around 51 Pegasi, a sun-like star about 50 light-years away. The detection itself was historic. For the first time, a planet had been convincingly identified orbiting a normal main-sequence star beyond the solar system. But the real shock lay in what sort of planet it seemed to be. 51 Pegasi b was not what many theorists had pictured when they imagined another planetary system. It appeared to be a giant world, about half the mass of Jupiter, yet orbiting astonishingly close to its star, completing a year in just over 4 days. A giant planet was not supposed to sit there, huddled so near its sun in a blistering orbit. In our own solar system, the gas giants live far out, beyond the rocky planets, in colder regions where their formation made intuitive sense under prevailing models. Here, suddenly, was something that did not fit the neat architecture many had assumed to be typical. The first great exoplanet discovery did not reassure theory. It unsettled it. That pattern would repeat throughout the exoplanet revolution. The earliest major success did not reward expectation. It exposed it. Soon the phrase hot Jupiter entered the vocabulary, and with it came a transformation in scientific feeling. Planetary systems could be genuinely strange. They did not need to resemble the solar system in order to be real. That may sound obvious now, but at the time it marked a subtle psychological rupture. Earth had long since been displaced from the center of the cosmos. Yet the solar system still retained a quiet role as template. Even when humans imagined other worlds, they often did so by varying a familiar arrangement. 51 Pegasi b weakened that comfort. Nature was under no obligation to build elsewhere according to local habit. The discovery sharpened another realization. If one giant planet could be found so close to its star, then perhaps planetary formation, migration, and orbital history were far more dynamic than earlier models had allowed. Worlds could move, systems could rearrange themselves. Stability might be harder won, and diversity much greater than anyone had assumed when only one planetary family was known in detail. Each confirmed detection widened the inventory of possibility. Some planets proved more massive than Jupiter. Others traced eccentric paths rather than nearly circular ones. The growing catalog did more than add numbers. It dismantled parochialism. There is something especially powerful in the moment when an intellectual possibility becomes a demographic fact. Before exoplanets were found, one could still debate whether planets were common, whether solar systems were a normal byproduct of star formation or something more contingent. Once detections multiplied, the emotional landscape changed. This was no longer a thought experiment. It was a census in progress. Even the early catalog, biased toward the large and easy to detect, hinted that the galaxy might be far more populated with planets than people had yet dared to feel in their bones. Other methods soon joined radial velocity and amplified the change. One of the most elegant was the transit method. Instead of watching a star wobble under a planet's gravitational tug, astronomers watched for the tiny dip in starlight that occurred when a planet passed in front of the star from our line of sight. The drop was minute and required exquisite measurement. But if observed repeatedly, it could reveal an orbiting body with unusual clarity. Better still, transits made it possible to estimate a planet's size. And, when combined with radial velocity, sometimes even its density, a world could emerge not just as an inferred mass, but as a physical object with dimensions and composition clues. As these methods improved, the sense of threshold intensified. Planet hunting was no longer speculative fringe work. It was becoming a mature field with surveys, competing teams, instruments, catalogs, and a rapidly evolving statistical horizon. The search for life beyond Earth was quietly undergoing one of its most consequential shifts. Earlier generations had asked whether there might be other worlds. Increasingly, the answer seemed to be yes. The question was migrating from existence to character. Then came Kepler, launched by NASA in 2009. The Kepler Space Telescope did not roam the sky chasing dramatic curiosities. Its strategy was patient, almost monastic. It stared at a single region of the Milky Way for years, monitoring the brightness of more than 150 zero stars, waiting for the faint repeated dimming that might signal transiting planets. Kepler's power came from scale and persistence. It was designed not simply to find individual worlds, but to answer a larger statistical question. How common are planets, especially small, rocky ones? How often do stars host worlds in regions where temperatures might allow liquid water at the surface? After centuries of imagining and more than a decade of early detections, astronomy was finally preparing to count the kinds of places where habitability might plausibly arise. The patience of the mission deserves notice. There is a romantic version of discovery in which revelation arrives suddenly, in one sharp moment. Kepler belonged to another tradition. Its greatness lay in repetition, in the long discipline of watching starlight and trusting that patterns too subtle for human senses would gradually disclose a deeper abundance. Night after night, month after month, year after year, it gathered tiny dips in brightness that, on their own, might mean very little, but together would redraw humanity's sense of the galaxy. And redraw it, Kepler did. The results that emerged were astonishing, not because they revealed one perfect Earth twin, but because they changed the baseline assumptions of the entire conversation. Planets were everywhere. Small planets were common. Multi-planet systems were common. Rocky worlds were not exotic exceptions. Some orbited within what astronomers called the habitable zone of their stars, where temperatures might allow liquid water under the right atmospheric conditions. The caveats remained enormous. Of course, habitable is not the same as inhabited. A planet of the right size at the right distance can still be sterile, frozen, scorched, suffocated, or chemically hostile. But the sheer abundance of candidates altered the emotional mathematics of the question. A universe in which planets are scarce preserves one kind of loneliness. A universe in which planets are ordinary creates another kind of possibility. For the public, Kepler also gave the imagination objects. These were not vague many worlds in the old philosophical sense, nor symbolic planets in fiction, nor disputed interpretations of Martian soil. They were entries in a growing celestial geography. Kepler 22b, Kepler 186 LEF, Kepler 452b. Worlds with measured orbits and estimated sizes. Worlds that could be described, compared, and placed into family resemblance. Humanity was no longer limited to wondering whether planets existed beyond the solar system. It could begin asking what kinds of planets there were, which stars hosted them, and how diverse planetary architectures might be. That new geography changed scientific ambition too. Once exoplanets had been established in large numbers, the focus naturally moved toward atmosphere, composition, climate, and biosignatures. But even before those later techniques matured, the census itself had already done something profound. It had weakened one of the oldest forms of cosmic exceptionalism. Earth might still be rare in its exact combination of properties. Complex life might still be uncommon. Intelligence might still be vanishingly improbable. Yet the stage on which those possibilities would play out had become vastly larger than previous generations had known in evidence-based terms. The galaxy was not a sparse expanse of lonely stars. It was full of systems, many of them likely carrying worlds. Then, in 2017, another discovery gave that reality a more intimate and almost architectural form. Astronomers announced the TRAPPIST-1 system, centered on a faint ultra-cool dwarf star around 40 light-years away, around which 7 Earth-sized planets were found. Several appeared to orbit in or near the star's habitable zone. The system was compact, tightly arranged, and unlike the solar system in many respects, yet instantly compelling. Here was not one possible rocky world, but a family of them, gathered around a single star, close enough in arrangement to feel almost like beads on a string. It is hard to overstate the imaginative power of TRAPPIST-1. Kepler had given the public statistics. TRAPPIST-1 gave it a scene. Artists rendered the planets from one another's skies. News reports invited people to imagine standing on one rocky world and seeing its siblings hanging large above the horizon. Scientists, properly cautious, reminded everyone of the unknowns. Stellar activity, tidal locking, atmospheric erosion. All the ways habitability can be complicated around small red stars. Yet caution did not erase the broader shift. The question, are there other, potentially Earth-sized worlds, had acquired a vivid and memorable answer. There is a subtle irony here. The more exoplanets astronomers found, the less the solar system resembled a universal model. Some systems were compact, beyond anything local. Others were dominated by large close-in planets or wildly eccentric orbits. Stars smaller and redder than the Sun hosted arrangements that once would have seemed improbable. Diversity, not familiarity, became the rule. Yet within that diversity, one encouraging thread kept returning. Rocky planets of roughly Earth-like scale seemed common enough that habitability could no longer be dismissed as a cosmic fluke. We still did not know how often life begins, but the number of possible laboratories in which it might begin was exploding. That expansion had a quiet, emotional consequence for generations. The question of whether we are alone had been buffered by ignorance. One could always imagine that the universe simply did not offer many suitable places. Kepler, TRAPPIST-1. And the wider exoplanet revolution did not prove that life is common, much less intelligence. But they made one older refuge harder to maintain. The galaxy now seemed rich in worlds. Abundance had entered the conversation as a fact, and abundance did not soothe the mystery. It sharpened it. Because once you accept that planets are ordinary, and that some rocky worlds likely sit in conditions where water and chemistry might become interesting, silence begins to feel different. Earlier ages could imagine that the heavens were empty because they offered too few places for life to begin. Now the heavens appeared to contain countless opportunities, even if only a small fraction were suitable. The numbers remained immense. That did not guarantee company, but it made the absence of clear company feel less trivial. Astronomy, in other words, had performed a strange reversal. It expanded the number of conceivable homes for life, while leaving the central question unresolved. The result was not closure, but pressure. More worlds meant more room for life, but also more room for absence. And as the catalog continued to grow, another line of thought, older than Kepler and older even than the first exoplanet detections, began to sound more haunting than before. If the galaxy is so full of places, then where is everybody? Once the galaxy had filled with worlds, the silence changed character. Before the exoplanet era, absence could still hide inside ignorance. Perhaps there were very few planets. Perhaps Earth belonged to an uncommon arrangement, and solitude followed naturally from scarcity. But that shelter had weakened. The numbers were no longer small enough to make loneliness feel easy. Astronomy had revealed a cosmos rich in stars, rich in systems, rich in places where rock, atmosphere, chemistry, and time might gather into something interesting. And yet no unmistakable signal had arrived. No alien engineering stood plainly in view. No radio beacon had endured verification. The old question did not fade in the face of abundance. It sharpened. That sharpening is often gathered under a name that has itself become part of the story: the Fermi paradox. The label suggests a single polished insight, but the history is somewhat untidier. The central remark is associated with Enrico Fermi, whose mind was famous for speed, clarity, and ruthless simplicity. In 1950, during a lunch conversation at Los Alamos, Fermi is said to have cut through a discussion of extraterrestrials and interstellar travel with a blunt question: where is everybody? Different recollections vary, and historians have noted that the fully elaborated paradox often attributed to Fermi took shape only later. But the spirit of the question remains the same. If the universe offers so many opportunities for life and intelligence, why does the evidence feel so absent? Part of the question's power lies in its plainness. It does not require advanced mathematics to be unsettling. A galaxy billions of years old contains immense stretches of time in which civilizations, if they arise at all, might spread, signal, build, or leave traces. Even allowing for the rarity of life and the difficulty of interstellar travel, it seems as though there ought to be room for something more than silence. The point is not that alien civilizations must be everywhere. It is that the gap between possibility and observation feels large enough to demand explanation. Later thinkers sharpened that unease into more explicit forms. In the 1970s, Michael Hart argued that if intelligent civilizations capable of interstellar expansion existed elsewhere in the Milky Way, then the galaxy should already bear signs of their presence. Frank Tipler extended related reasoning even further. In that harder formulation, the issue becomes less a paradox than a pressure point. Given enough time, why has no civilization visibly crossed the stars, colonized the galaxy, or left incontrovertible artifacts behind? Historians and philosophers have therefore sometimes suggested that Fermi paradox is a slightly misleading label. Fermi voiced the memorable question. Hart and Tipler helped sharpen the more rigid version attached to it. But whatever name one prefers, the discomfort remains. There are many ways to answer, and the sheer variety of them tells its own story. Some begin by lowering expectations. Perhaps intelligent life is extraordinarily rare. Rarer than early optimists or even the exoplanet revolution encourage people to believe. This line found one of its most influential popular formulations in the rare Earth hypothesis, advanced by Peter Ward and Donald Brownlee around the turn of the millennium. Their argument did not deny that microbial life might arise more readily. It focused instead on the long chain of conditions that may be required for complex, animal-like, technologically capable life to emerge and persist. A stable star, a suitable orbit, long-term climate regulation, plate tectonics, a helpful planetary architecture, a favorable galactic environment. In their telling, the chain becomes daunting. Rare Earth appealed to many because it restored gravity to Earth's history. It reminded people that life is not only chemistry in a puddle. Complex biospheres grow through contingency layered on contingency. Yet the hypothesis also revealed how quickly cosmic debates become arguments about which uncertainties deserve the most emphasis. Some researchers accepted the general caution, but resisted strong conclusions about rarity, pointing out how little sample size humanity actually possessed. One inhabited planet is not much of a database. Others suggested that Earth's history may look uniquely intricate only because it is the only biosphere we know in detail. If more examples existed for comparison, perhaps some conditions now treated as exceptional would no longer appear so singular. Another family of answers does not make intelligence rare so much as fragile. In this view, Civilizations may arise often enough, but technological cultures do not remain detectable for very long. They exhaust resources, destabilize themselves, destroy themselves in war, retreat from outward expansion, or pass through radio-loud phases too brief to overlap with ours. Silence then becomes a matter of timing rather than existence. Civilizations may bloom and vanish like sparks in different eras of the galaxy, with so little overlap that mutual detection becomes improbable. This idea has a special psychological pull because it turns the cosmic mystery back toward humanity. We are no longer asking only whether others exist. We are asking what becomes of a technical species after it acquires power. There is something sobering in that turn. It asks us to imagine the galaxy not as a serene library of advanced wisdom, but as a place where intelligence may be common enough to arise and common enough to fail. Under those conditions, silence would not mean emptiness. It would mean transience. Other responses are stranger in tone, though not necessarily less serious. The so-called zoo hypothesis imagines that advanced civilizations might know about Earth and intentionally avoid obvious contact, allowing younger worlds to develop without interference. Variants suggest quarantine, non-intervention, ethical restraint, or simple indifference to a still primitive species. Closely related possibilities replace secrecy with mismatch. Perhaps the signals are there, but not in forms we recognize, or not at scales and timescales that align with our instruments and expectations. A civilization far older than ours might not broadcast with obvious radio leakage. It might communicate too efficiently, too rarely, or in ways we have not yet learned to hear. These ideas often hover near the edge of scientific respectability because they are so difficult to test, yet their persistence is revealing. They show how strongly the mind resists a fully barren conclusion once abundance has been admitted. If the galaxy is rich in worlds, and if life and intelligence feel even modestly plausible, then silence begins to invite narrative, hidden observers, selection effects, deep time gaps, zones of non-overlap, civilizational etiquette. The paradox generates not only equations, but thought experiments about consciousness, culture, and the limits of human expectation. At the same time, more austere thinkers prefer to dissolve the mystery rather than multiply stories. Perhaps the answer is simply that interstellar travel is much harder than early speculation allowed, and that the visible traces of technological civilizations are far subtler than humans once assumed. A galaxy can be full of inhabited planets and still appear quiet if each civilization remains largely local. Radio emissions weaken. Expansion may be unattractive or uneconomical. Engineering need not be spectacular. The contradiction then fades, not because others are absent, but because the assumption that they would be obvious turns out to have been naive. In that reading, silence tells us less about aliens than about our own habit of overestimating detectability. This widening field of explanations had an interesting effect on SETI itself. It turned the Enterprise into more than a technical search. It became a meeting place for astronomy, biology, sociology, history, anthropology, and philosophy. To ask why the sky seems quiet is to ask not only how many civilizations might exist, but what civilizations are like, how long they last, what they choose to do, and how human assumptions shape the very idea of evidence. The alien question, which began in antiquity as a challenge to cosmic centrality, had become a mirror for thinking about intelligence as a category of nature. Yet this intellectual richness existed alongside a very earthly problem. For much of the late 20th century, Serious work on extraterrestrial intelligence suffered under what researchers often called the giggle factor. The phrase sounds light, almost dismissive, but the consequences were real. To many outsiders, and even to many scientists in neighboring fields, SETI sounded uncomfortably close to science fiction, flying saucers, and the more sensational edges of popular culture. Respectable astronomers could speak about black holes or cosmic background radiation without social penalty, speak too openly about listening for alien civilizations, and the tone around the room could change. Careers, especially young ones, are sensitive to that shift. The stigma was not entirely irrational. The history of the subject had given the public many reasons to confuse scientific CT with less disciplined claims. Media fascination with UFOs, contacté culture, and speculative entertainment blurred boundaries. But the damage fell unevenly. Researchers working carefully with radio telescopes, statistics, and sober criteria inherited suspicion from ideas they did not endorse. In a field dependent on institutional trust, ridicule could act as a real constraint. It affects funding, conference tone, hiring, and the willingness of scientists to attach their reputations to a question that may take decades to answer. No one illustrates that terrain better than Jill Tarter. Trained as an astronomer and increasingly central to SETI from the 1970s onward, she brought a combination of technical seriousness, resilience, and public clarity the field badly needed. Tarter could speak about the search for extraterrestrial intelligence without collapsing into apology or overblown promise. She understood both the scientific problem and the sociology surrounding it. Part of what made her important was not only the research she helped lead, but the steadiness with which she inhabited a question many people treated as unserious unless it produced immediate results. That steadiness became especially important in the early 1990s. NASA had finally begun a more ambitious microwave search program, the High-Resolution Microwave Survey, launched in 1992 after years of planning. Symbolically, it mattered a great deal. Federal support suggested that SETI had won a measure of legitimacy within official science. The search was still uncertain, still difficult, but no longer merely a romantic side pursuit. Yet that legitimacy proved fragile. In 1993, after only a year, Congress terminated NASA's funding for the program. Senator Richard Bryan of Nevada mocked the effort as a great Martian chase, and the cancellation became one of the most famous setbacks in SETI's history. The details are worth lingering over because they reveal how scientific questions can be shaped by politics, image, and timing rather than evidence. The search had not failed experimentally in any meaningful sense. It had barely begun, nor was it canceled because radio astronomy had disproven extraterrestrial intelligence. It was cut because the optics were vulnerable. In a political culture attentive to spending and eager for ridicule, SETI made an easy target. The lesson was harsh. A field can be methodologically serious and still lack the cultural armor required to survive public mockery, and yet the search did not disappear. It adapted. Private support, especially through the CT Institute and later initiatives, allowed work to continue in new forms. Project Phoenix, launched in the mid-1990s, pursued targeted radio searches with funding outside the federal structure that had just withdrawn. The focus narrowed to nearby sun-like stars, and much of the practical spirit of the earlier program survived. This persistence matters because it shows how scientific communities endure through institutional reinvention. When one channel closes, committed researchers sometimes build another. The question remained too intellectually compelling, too methodologically real, to vanish merely because it had become politically unfashionable. Tarter was central to that continuity. Her leadership helped keep the field organized during a period when it could easily have fragmented into discouragement. There is a particular form of endurance visible here. It is not the drama of a lone genius, nor the triumph of a breakthrough, but the quieter persistence of people who refuse to let a valid question disappear simply because it attracts laughter. That endurance rarely receives the same attention as discovery, yet it is often what makes future discovery possible. By this point, silence had acquired multiple layers. It was an astrophysical mystery, certainly, but also a social one. Why the universe felt quiet was bound up not only with the possible rarity or fragility of civilizations, but with humanity's difficulty sustaining a search that could run for decades without reward. Where is everybody? Was no longer addressed only to the stars. In a quieter way, it was directed inward, toward scientific culture itself. How seriously can a civilization take a question that offers no quick answer, no immediate proof, and a high risk of embarrassment? There is a deeper irony in that. The more exoplanets astronomy found, the more plausible extraterrestrial life seemed in broad outline, and the more direct absence stood out. One might expect abundance to make searching easier to justify. In some circles, it did. Yet the old discomfort lingered. Large questions attract longing, and longing can make professionals uneasy. In fields where evidence remains thin, the fear of self-deception often travels beside the fear of ridicule. So this section of the story is not really about a single paradox with a single clean answer. It is about a transformation in the meaning of silence. Earlier silence could be blamed on ignorance. Later silence had to coexist with abundance. Earlier silence was mainly observational. Later silence became philosophical, sociological, and existential as well. It invited theories of rarity, collapse, timing, non-overlap, indifference, hiddenness. It also forced the human search itself to become more self-aware, more careful about its assumptions, and more conscious of its cultural vulnerability. Still, silence is not the same thing as stillness. While Radio SETI wrestled with absence and legitimacy, other lines of inquiry continued to evolve. Planetary science was rethinking habitability. Exoplanet research was moving from detection toward chemistry and atmosphere. Ocean worlds within our own solar system were beginning to look newly promising. Across these different domains, a quieter change was taking place. Scientists were becoming more cautious about what would count as evidence of life, and at the same time, more ambitious about how such evidence might one day be found. In a sense, that was the only mature response the long silence could produce. Not surrender, and not proclamation, but refinement. The next phase of the search would not rely on a single dramatic signal or a philosophical argument about absence. It would ask a subtler question. If the universe has not announced its company in obvious ways, how careful must we become in learning to recognize life when it leaves only the faintest trace? So the search entered a quieter kind of maturity after false alarms, disputed experiments, proliferating planets, and the long philosophical pressure of silence. Scientists were left with a harder form of hope. It was no longer enough to ask whether life might exist elsewhere. The more demanding question was how life would appear in the data if it did exist, and how one could recognize it without repeating the old human error of seeing meaning too quickly. The future of this inquiry would depend on restraint as much as imagination. That shift can be felt across modern astrobiology. In earlier eras, the search often leaned on singular moments, a line on Mars, a strange radio pulse, a surprising experiment in Martian soil. Contemporary researchers still welcome striking anomalies, of course, but they have become more explicit about the danger of overinterpretation. One molecule in an atmosphere is not enough. One odd chemical imbalance is not enough. Even a suggestive combination of signs may not be enough unless the planetary context is understood in unusual depth. The field has learned, sometimes painfully, that life detection is not a matter of finding one magical clue. It is a matter of building a case strong enough to survive every plausible, non-biological alternative. That is why the modern idea of a biosignature is both powerful and slippery. In the broadest sense, a biosignature is any feature, substance, pattern, or phenomenon that might point toward living activity. On Earth, life reshapes atmospheres, cycles carbon, releases gases, alters minerals, changes surfaces, and leaves layered chemical consequences behind. Looking outward, scientists naturally ask whether similar traces might be found on other worlds. But the difficulty appears almost at once. Biology can produce oxygen, methane, or atmospheric disequilibrium. So can non-biological processes under the right conditions. A clue that feels compelling in isolation may become ambiguous once one accounts for volcanism, photochemistry, stellar radiation, planetary mass, ocean loss, or geologic history. In other words, context has become everything. That is one reason NASA and other institutions have spent recent years developing more formal frameworks for evaluating possible evidence of life. The point is not bureaucratic caution for its own sake. It is an acknowledgement that if the answer ever begins to emerge, it may do so gradually, by degrees of confidence rather than in a single dramatic moment. Researchers have proposed scales by which evidence can be judged, not because they want to weaken discovery, but because they want to preserve credibility when the first strong yet incomplete signals arrive. In a field shaped by centuries of projection, and by a modern media environment that amplifies premature certainty, such frameworks function almost like intellectual self-defense. The search for life in exoplanet atmospheres makes that especially clear. With telescopes such as Hubble, and more recently the James Webb Space Telescope, astronomers have learned to analyze the light passing through or emitted by planetary atmospheres with astonishing sensitivity. A world crossing its star can allow a thin fraction of starlight to filter through its gaseous envelope, leaving spectral fingerprints that hint at composition: carbon dioxide, methane, water vapor, perhaps more. These are no longer fantasies. They are real observational targets. Yet precisely because the data have become more powerful, interpretation has grown more delicate. A planet is never just a list of molecules. It is a system, and systems can deceive when viewed in fragments. K218b has become one of the clearest examples of that new uncertainty. It is not an Earth twin. It is larger, more massive, and unlike anything in our own solar system, yet it orbits within a region where temperatures might permit liquid water. And observations have suggested the presence of molecules such as methane and carbon dioxide in its atmosphere. At various moments, speculation around the planet intensified, especially when additional signals were proposed that might, on Earth, be associated with life. Public excitement rose quickly. So did caution. Scientists began reminding one another. And everyone else? How many assumptions still stand between a spectral feature and a claim about biology? The K218b episode is revealing because it condenses so many themes from the longer history. A distant world appears promising. The data are real. The measurements are sophisticated. The interpretation is plausible enough to attract attention. Then the discipline reasserts itself. Are there other explanations? How secure is the signal extraction? What atmospheric model is being assumed? Could unfamiliar chemistry imitate a living world? Even when a planet becomes a serious candidate for further study, the language of the field remains careful, conditional, and provisional. That is not weakness. It is maturity. There is a kind of dignity in that restraint. Modern astrobiology is ambitious, but not innocent. It no longer imagines that life will announce itself in a form designed for human emotional satisfaction. If anything, the most likely future looks more difficult than that. Evidence may first arrive as an atmospheric oddity that survives many rounds of criticism, or as a pattern of compounds that becomes steadily harder to explain without biology, or as a convergence among chemistry, geology, and energy gradients on a nearby world. None of these would feel like the old fantasy of a crisp extraterrestrial greeting. They would feel like science learning to live with the approach of an answer before the answer is fully secure. That same seriousness has widened the range of places considered biologically interesting. For much of the 20th century, Mars held a privileged position because it seemed accessible, somewhat familiar, and historically charged. It still matters enormously. Yet over recent decades, astrobiological imagination has expanded toward ocean worlds, places where liquid water may exist not under an open sky, but beneath ice. Europa, orbiting Jupiter, and Enceladus, orbiting Saturn, have become central to that shift. These are not worlds that invite Lowell-like fantasies of surface civilization. Their appeal is subtler, more chemical, more hidden, and for that very reason perhaps more realistic. Europa has long suggested concealed potential. Beneath its cracked icy shell lies compelling evidence for a global subsurface ocean, kept liquid by tidal heating as Jupiter's gravity flexes the moon's interior. Water, energy, chemistry, the ingredients are at least conceptually present. Enceladus went further when the Cassini mission observed plumes of water vapor and ice grains erupting from fractures near its south pole. Instead of imagining an ocean buried beneath miles of ice with no direct access, scientists suddenly had material from such an ocean spraying into space. Cassini's data revealed water, salts, organic compounds, molecular hydrogen, and later evidence suggesting phosphorus in plume grains. None of that proves life. But it makes Enceladus feel less like an abstract possibility and more like a natural laboratory where habitability can be investigated unusually closely. Notice the vocabulary that dominates here. Not life. Yet, habitability, organics, salts, energy gradients, water-rock interaction. Scientists have become attentive to the fact that a world does not need to resemble Earth's surface to be biologically interesting. Life, if it arises elsewhere, may prefer niches more hidden than the landscapes earlier human imagination found easiest to romanticize. An ocean beneath ice is harder to picture than a canal-crossed Mars, but perhaps closer to reality. The search has grown less anthropomorphic in the process. It no longer asks so insistently for places where humans could stroll. It asks for environments where chemistry has enough continuity, complexity, and available energy to become something more. That distinction helps explain the wording around missions, such as Europa Clipper. It is not described as a direct life detection mission in the simplest sense. It is designed to assess habitability, to map the ice shell, investigate the ocean, characterize the moon's chemistry, and determine how favorable the environment might be for biology. To an impatient public, that can sound like hesitation. In fact, it reflects methodological wisdom. Life detection without environmental context is fragile. Habitability studies prepare the ground on which a later claim, if it ever comes, might stand more securely. The field is learning not to skip steps merely because the longing is old. Meanwhile, beyond the solar system, another dream is taking institutional form. Future observatories are being imagined not simply to count planets or identify atmospheres, but to search more directly for signs of life on Earth, like worlds around other stars. NASA's Habitable Worlds Observatory is the clearest symbol of that ambition, still in planning rather than operation. It represents a profound change in human intent. For centuries, other worlds were philosophical possibilities. Then they became astronomical detections. Now the idea is to build an observatory whose purpose includes examining whether some of those distant worlds bear atmospheric evidence suggestive of biology. The ancient question is being designed into the hardware of the future. And yet, even here, caution is built into the ambition itself. No serious researcher imagines such an observatory will point at a planet and instantly announce extraterrestrial life with cinematic clarity. The likely reality is slower, layered, and difficult. Some targets will look promising and then less so. Some atmospheres will resist clear interpretation. Biosignature candidates will need repeated scrutiny, modeling, cross-checking, and argument. A mature field expects ambiguity, not as a failure, but as the ordinary condition of difficult knowledge. Running alongside all of this is another thread, older in spirit and still unresolved in ethics. For most of this documentary, the search has been framed as listening, detecting, inferring, and testing. But humanity has never been satisfied merely to listen. Again and again, it has tried to speak. In 1974, from the Arecibo Observatory in Puerto Rico, a message was transmitted toward the globular cluster M13. It was more symbolic than practical, given the enormous distance involved. But symbolism matters. Encoded in the message were numbers, chemistry, DNA, a human figure, the solar system, and the telescope itself. The gesture was less an attempt at real-time conversation than a declaration of presence. We are here. We know enough to send pattern into the dark. That gesture had companions. The Pioneer plaques, attached to spacecraft in the early 1970s, carried engraved depictions of human beings, the solar system, and a map locating the sun by nearby pulsars. The Voyager Golden Record followed in 1977 with a broader ambition, gathering sounds, music, greetings in many languages, and images of Earth. These artifacts remain moving even when one knows how unlikely they are ever to be found. They reveal that the question, "Are we alone?" has always carried a counterpart. If we are not alone, how would we introduce ourselves? And perhaps more unsettlingly, what do we choose to say before we know who is listening? That last question remains contentious. Some researchers and philosophers argue that actively transmitting messages to the stars, sometimes called METI, involves risks that should not be assumed lightly by a small number of people without broad international discussion. Others counter that Earth has already been radiating signals into space for decades. and that deliberate messages add little danger while honoring a profound human impulse toward contact. Beneath the policy arguments lies something older and harder to settle. Listening feels cautious. Speaking feels consequential. It turns the search from inquiry into exposure. SETI's own protocols reflect that seriousness. The expectation, at least in principle, is that if a credible extraterrestrial signal were ever detected, no reply should be sent casually or unilaterally. Verification, consultation, and international consideration would matter. That tells us something about the psychological evolution of the field. At first, the mystery centered on whether anyone else existed. Now, the question also includes what kind of civilization humanity wishes to be in relation to that possibility. Curious, eager, prudent, reckless, humble, exposed. In the end, the careful future of not knowing is not empty. It is crowded with better instruments, subtler methods, more sophisticated skepticism, and a widening sense of where life might hide. It includes ocean worlds under ice, atmospheres around planets circling dim red stars, laboratory frameworks for evaluating weak signals, and observatories previous generations could barely imagine. At the same time, it preserves something ancient. Human beings are still standing beneath the same dark, asking whether the universe contains other minds, and still finding that the act of asking changes them. Perhaps that is why the search has endured through so many phases of error and patience. It is not sustained only by optimism. It is sustained by the recognition that the question is large enough to refine the people who pursue it. To search carefully for life elsewhere is to become more disciplined about evidence, more humble about assumption, and more aware of how quickly meaning can be projected into the unknown. Science, in that sense, does not merely move toward an answer. It reshapes the searcher, and so we arrive at a final threshold. Not necessarily the threshold of discovery, though that may still lie ahead, but the threshold of perspective. The universe is no longer a blank backdrop against which humans imagine companions out of loneliness. It is a place crowded with real worlds, hidden possibilities, and unanswered signals, approached by a species that has learned, slowly and imperfectly, how to wonder without surrendering its standards. Whether the first decisive evidence comes from an icy moon, a distant atmosphere, or some signal we have not yet learned how to recognize, it will meet a humanity already changed by the long discipline of waiting, which may be why the deepest meaning of the search has never been only the answer it hopes to find, but the kind of mind it requires while the darkness is still, for now, mostly quiet. After all the telescopes, the equations, the false alarms, the Martian hopes, and the signals that flared and vanished, the central idea remains strangely untouched in one sense and completely transformed in another. We still ask whether life exists beyond Earth, but we no longer ask it in the same way. The question has grown more careful. It has become less a matter of imagination alone, and more a test of how human beings learn to live with uncertainty. We have discovered that the universe is richer than earlier generations were able to prove, filled with planets, hidden oceans, complex chemistry, and possibilities that once belonged only to thought. And yet, the deeper our tools reach, the more clearly we see how difficult it is to separate wonder from evidence. That may be one of the most important things this search has revealed. Science is not only a machine for producing answers, it is also a discipline for resisting the answers we are too eager to accept. It asks us to become more precise, more patient, more humble than our first instincts allow. In that sense, The search for life beyond Earth has already changed us, even without a final detection. It has forced us to look at our own minds while looking outward, to notice how readily we project meaning into the unknown, and how much care is required to meet reality on its own terms. Perhaps that is why the question still feels so powerful. It is not only about distant civilizations, biology under alien skies, or a signal crossing the dark between stars. It is also about what kind of species we are while we wait. We are the beings who build instruments to listen into silence, who send small messages outward, who keep asking even when the answer does not come quickly. And somewhere in that long, patient act of asking, there is already something profound. Whether the universe is full of life, or whether it is in ways we still struggle to imagine, mostly quiet. The search itself has become part of how humanity learns its place in the dark,